Hi, and welcome to this first lecture where we're going to be talking about units, dimensions, measurements, and scaling. So, units are necessary to understand the measurements that we make, because without them, our measurements would be practically useless because we wouldn't know if we were measuring someone's height, weight, a car's speed, and so on if we didn't have units. So we need units to be able to contextualize measurements and to give us a sense of what we're getting. And so we make it easy with the three fundamental physics quantities and their SI units, or International System of Units. So here we have the length, where we represent it with a capital L, and its units is the meter, represented with a lowercase m. And then we also have time, represented with uppercase T, measured in seconds, and mass, measured in kilograms. Now, we also have other units in our everyday life that we have derived for convenience, like pounds in America, centimeters, miles, kilometers, but not all of them are easy to work with here. Like, think about it. It'd be a big headache if you had to convert between feet, inches, centimeters, yards, and miles all the time. So we choose to stick with one. And other physics quantities can be derived from these fundamental quantities and have their dimensions. And we denote dimensions with brackets. So for example, here, brackets around speed would mean the dimensions of speed. And here we have a couple of examples. So speed, the dimensions of speed are the dimensions of length divided by the dimensions of time. In this case, we would have meters per second. And the dimensions of volume are the dimensions of length cubed, or meters cubed. And density, which is mass over volume, would have the dimensions of mass over volume, or mass over length cubed. And a very important dimension that we should know in physics is the dimension of acceleration, which is given by the dimensions of length over the dimensions of time squared, or in units meters per second squared, so on and so forth. I think you get the hang of it. And you can basically derive all other quantities from the fundamental quantities that we went over on the last slide. And using these dimensions, we can now make measurements. And in measurements, it's really important that you include the uncertainty, because without the uncertainty, your measurement would practically mean nothing. Uncertainty is like the plus or minus you see at the end of measurements. Like if you were measuring someone's height, maybe it would be 163.9 centimeters plus minus 0.1 centimeters. It's kind of like a range of uncertainty where the height would be included, but you're not sure where in the range it's included. Okay, so using dimensions, we can make scaling arguments. And let's say you have a giraffe with neck length L and size S. We'd probably assume that L is proportional to S, meaning that as the giraffe gets larger, its neck length would also get longer in proportion. And we'd also think that mass is proportional to size cubed because of volume, which is length cubed. So what does this tell us exactly? It tells us that if we are given two giraffes, one of which is 5 times larger than another, then its neck would be approximately 5 times longer, and its mass would be about 125 times larger of the other giraffe. So this is very important when we're making comparisons and connections between different measurements and dimensions, and it can help us a lot and give us a lot of information about our measurements. So that was quite a short lesson, but given that it's the first one, I hope that we all learned a little bit about units, dimensions, uncertainty, measurements, and scaling arguments, all of which form the basis for the future of physics.